Up here.
Oh,
That's a real
that's right. That's the.
They may complain. We say, wow, if you don't trust everything, ignore this. Hook back on it. And now I think it will work forward, backward.
Oh, okay, good. Okay, good. Thank you. Thank you.
All right. So we're happy to have Ting-Wai Chiu visiting us from Taiwan University. Ting-Wai is an expert on lattice QCD, and he has some creative version of domain wall fermion, which is kind of a tower fermions. He calls that the optimal domain wall fermions. And he has used that to study quite a bit of the heavy quarks spectrums and so on. Now he's extending that to find the temperatures. Oh, we'll be happy to see what you have.
Okay. Thank you very much. Yeah. I would like to talk about the symmetry in high temperature QCD. Okay. And I would like to use the meson, the degenerates of the meson correlator, okay, to examine the restoration of chiral symmetry in high temperature QCD. And then, in this study, okay, I find the hierarchic restoration of chiral symmetries from SU2 times SU2 times U1A to SU3 times SU3 times U1A, and then from to SU4 times SU4 times U1A. Okay, as I can increase the temperature successively from say 190 MeV to 1540 MeV. So, this is outline on top. First, I will review the role of symmetry in physics, just with a few examples. Okay. Then I will discuss the symmetry and the degenerates of the meson C correlator. And then I define the symmetry parameter to measure the symmetry. Okay. Then I will briefly outline the simulation of NF2 plus 1 lattice QCD at the physical point. And then I show you the results of the meson C correlator and also the symmetry parameters, okay, of the various paper contents, okay, from light mesons to heavy mesons. Okay. Then I will show you the hierarchic restorations of chiral symmetry from my data. Okay. And finally, I will summarize the results in conclusion. Okay. I think everyone agrees, okay, symmetry plays an important role in physics. Yeah, just a few examples. For example, the translation invariance, okay, gives us the conservation of momentum. Okay? And the rotational invariance gives us the conservation of angular momentum. Okay? And the general principle of relativity gives us the general relativity. Okay? And the gauge symmetry, okay, is the underlying principle of all fundamental inductions, say QED, electroweak theory, and QCD. Okay, and let's see.
Yeah, it's hard to see.
It
doesn't work so well on the.
It doesn't. Okay. It's on, but then.
one sees it.
But no one sees it. Okay, so I don't use it.
Can you use
Okay.
No, there is a pointer.
Yeah,
There's
okay.
a real pointer.
Okay, good.
people cannot see
Yeah.
those.
So, can you recognize this guy?
That's what I was wondering.
Can you recognize this guy?
Sure.
Huh? No? Herman Wai.
Oh, why? Okay.
Everyone.
Why? Weyl. Okay, so the others, you know, okay, this Yan Yang, you know, okay, yeah. And the spontaneous broken chiral symmetry. So this is not a perfect symmetry, okay, it's the spontaneous broken, okay, by the vacuum of QCD, okay. But it was recognized by Alan Wu a long time ago, okay, in 1960 or so. And of course, in the context of the QCD, then becomes more clear, okay, and give us the low engine physics of the strong interaction. Now let's go to higher temperature, okay. So I think everyone would agree, say, restorations of Chiu symmetry at high temperature QCD will give us the dissolution of hadrons into quark-1 plasma. Okay. So what I want to add in this picture is that hierarchic restoration of Chiu symmetry at high temperature QCD, and this will imply the hierarchic dissolution of hadrons into quark-1 plasma. Okay. So that, yes.
Are you saying that deconfinement and chiral symmetry restoration are the same thing?
If I do not say exactly the same, okay, but it would occur closely, okay, at a temperature where I think it must occur at a temperature higher than the restoration of Chiu symmetry. After that, then it becomes dissolved. Okay, I'll give you a more precise definition later. Okay, yeah. So so the hierarchy, okay, yeah, of the restoration of Chiu symmetry, okay, will imply the same hierarchy for the hadron dissolution. Okay, yeah, that's what my claim. Okay. Yeah. Let's consider QCD with n massless quarks. Okay, and this action possesses the SUN left cos SUN right cos 1A Chiu symmetry. Okay. But at low temperature, okay, quarks are confined in the hadrons, and the Chiu symmetry is broken by the vacuum of QCD, and then with the non-zero Chiu condensate. Okay. Moreover, the UA1 symmetry is explicitly broken by the Chiu anomaly. Okay. So due to the quantum fluctuation of the non-trivial gauge configurations. Now, if I increase the temperature above the some temperature Tc0, okay, the zero here denotes the massless quarks. Okay, the quark condensate becomes zero. Okay, and the Chiu symmetry is restored at least the SUN cos SUN. Okay, yeah. And also the UA1 axial symmetry is also effectively restored due to the but it is at a temperature, say I call it T10. Okay, yeah, and due to the suppression of the quantum fluctuations of the topological non-trivial gauge configurations at high temperature. Okay, so this is already known a long time ago in 1980. Okay, in the picture of the instanton gas. Okay. But of course, this turns out to be agreed with the lattice QCD result, except there's an overall constant difference. Okay. Yeah, so far it's still an open question whether the T10 bigger than TC0, or they are more or less the same. Okay. So in the following, I just define this TC10, okay, as the maximum of the TC0 and T10. Okay. So that the SU2 cos SU2 cos U1 or SUN cos U1 are restored at T1 T0 C1. Okay. The same notation I also use for the massive quarks. Okay. So now let's consider QCD with physical.
I think you just touch the screen. It's like an iPad.
Oh, okay, great. This is the first time I see it. This is fantastic. Yeah.
Well, yes and no.
Yeah. Yeah, I never see such a large screen. Just like an iPad. Okay.
Doesn't reflect me.
Yeah, do it. Oh. Okay, great. Now consider QCD with physical UDSCP quarks. Okay. And since it has a mass, okay, the mass fits all the Chiu symmetry, okay. So it does not have the SUN cos U1 for any integer n from 2, 3, 4, 5. Okay, no. Okay, yeah.
A question.
Yes.
So after here, is the QCD anomaly included in the chiral symmetry here yet, or?
No. Yeah, it is not exactly the same. Okay.
Okay.
Yeah.
But they're not included in here, the QCD anomaly.
QCD anomaly, okay, already fit the UA1 explicitly, even in the massless limit, okay?
Yes.
So this have the mass there, additional breaking is there, okay? Yeah. So So here the action at the action level, okay, already fixed, okay, and it does not have the Chaos image or the UA1 image, even at the action level, not even include the consider the quantum corrections, okay, yeah, yeah. For the massless case, okay, if you have the UA1 Chaos UA1 image, access image, but the quantum correction, quantum fluctuations fix the UA1 image explicitly.
Yeah,
Okay. Now since the UDSCB, they are physical, so they have a hierarchy of the masses. Okay, from a few MeV to a few GeV. Okay. So as the temperature is increased successively, okay, and the Chaos image is expected to restore hierarchically, okay, from the SU2 cos SU2 cos U1 of the UD quark to the SU3 cos U1A Chaos image of the UDS, okay, and this temperature is at the for the SS bar. I will explain the location later, okay, yeah, and the SU4 cos U1, okay, at an even higher temperature, okay, and then SU5 cos U5 U1 at an even higher temperature. Yes.
Make a question?
Yes.
So wouldn't you expect that lower energies to lambda, the lambda parameter, to be also a relevant scale there? So I would expect that for temperatures, below the scale of QCD,
Below the
between the D and the S, okay, if you are a bit above.
Which one?
Between the first two.
First two.
Yeah.
This one, yeah, sure. Now is below the lambda, QCD, okay, yeah. But others are not.
No. The others I understand. It's
Yeah,
fine,
okay,
but I would.
Yeah.
Do you see this? The first one, the difference between the D bar D and the S bar S. The first two different.
Oh, D bar is presumably physically, okay. D is heavier than the U, okay.
No, sure.
Yeah.
Okay.
Yeah.
Sorry. Yeah. Thank you.
Yeah. Okay. So as I look at the literature, seems to me nobody discussed such a picture. Okay.
But when you talk about symmetry, you always think about approximate symmetries because you still have the quark masses at every temperature, right? So you never have a true symmetry.
Yeah,
I mean, the spontaneous symmetry breaking is gone, right? But that's what you claim. But I still have small corrections proportional to the quark masses, right?
Quark mass, but then even
if they are small compared to the temperature and so on.
Yeah, the reason is that because the quarks apply the thermal energy. Say,
Sure.
And then
IT is large compared to the mass.
When the thermal energy is much bigger than the mass, they need the mass is relevant. Okay. Yeah. But seems to me this is a rather direct or consequence. But seems to me no one discussed about that. Yeah, in the literature. Yeah, you notice anyone discuss this? Please let me know. Okay. Yeah. And this study will obtain the result. Okay. For this this TC, okay, is the the Chaos image restoration for this U bar D sector and that's less than the U bar S, and then the U bar C, and less than T SS bar, and then the less than the T S bar C, and then less than the C bar. Okay, so this is the numerically obtained result. Okay. One thing interesting is that for the SS bar, the temperature is higher than the U bar C. So you see, it's not just look at the mass, okay, of the meson or the mass of the quark, okay. You see, this has a heavy and light quark together, but then this Chaos image is restored earlier at lower temperature than the SS bar.
When you say chiral symmetry for U bar C, are you talking about the parity plus and minus partner of
Well, I will define this more precisely in terms of mesons correlator of two favor, okay, of two quarks, okay. Yeah, and there are many different manifestations. Say, for example, the parity, okay, okay. In terms of baryons, okay. Yeah, but I'm talking about the meson. And meson, I think, is sufficient to see the temperature at the Chaos image restoration.
I guess maybe my real question is, with a charm quark, what do you mean by chiral symmetry? Because once, clearly it's not like a pion.
Yeah.
Symmetry in the spectrum, I guess.
But
Yeah,
that's when
yeah.
you take the parity partners.
So the chiral symmetry, the restoration chiral symmetry I'm talking is in the context of the degeneracy of the meson T correlator.
Mhm.
Okay. So that is because the temperature is far higher than the mass, the quark mass. Okay, is a
It depends on how do you define it. I mean, normally at final temperature you define you have some kind of parameter,
Yeah.
All the parameter. I mean,
Yes.
normally it's the psi bar, psi.
Yeah.
You can probably calculate individually what is the UU bar, DD bar, SS bar. I'm sure that CC bar, the people have calculated SS bar up to S, but CC bar is there are no condensate.
No, there is.
Yeah, sure. You have a condensate. You can compute the condensate.
I know. Have that people calculated CC bar condensate and what is the value?
I don't remember.
Yeah.
Tiny.
And BB bar. And what about BB bar?
Sure, you can also compute it. Okay, no problem for the lattice QCD to compute.
And then you see temperature dependence.
I haven't looked at that myself.
Sure.
But-
Yes, sir. Sure.
Yeah.
When you look at, and then if you increase the temperature, then you see it is dropping. Okay, and it drops to 0, then you can see it.
So what is the value of CC bar?
You're on the condensate. Okay, I cannot tell you offhand. Okay. Yeah, but I can find out later. Okay.
I mean, okay.
Yeah.
So what is the relative value to the UU bar, DD bar condensate?
Oh, much higher. Say
Much higher.
More than, I say, 100 times or something like that.
Really?
I think that the
That's very.
That's just counterintuitive. I would have thought that the CC bar condensate should be much
First time I
smaller.
realized that even QQ bar, I mean, heavy quark CC bar have condensate, which is that large.
The thing,
Condensate is the one I'm talking about, not the chiral condensate, not taking the limit.
I'm talking about psi by psi.
Yeah, that's it.
That's
Okay.
chiral
So
condensate.
there's the trace of the inverse of the.
Yeah.
Quark
So you are
condensate
saying the
with
CC
the
bar
mass.
also has
Yeah,
a non-managed value, it's very
Yeah,
large.
yeah.
you look at the
Really?
Galvano-Strander relation, take overlap fermion and so on. You take the pseudoscalar CC bar, it has correlator, you integrate it over time and so on. That give you F pi and so on. And that's really the quark mass times the CC bar and condensate. That's for all quark masses. So from there you can infer what the CC bar is if you know the quark mass. Like the light quark Galvano-Strander, heavy quark
I know there is a spontaneous relation.
One question is that in these correlators, when you have two equal quarks, the S bar S and the CC bar, there is disconnected contributions in this computation. Do you compute this?
No, disconnect, I did not compute the disconnect contribution. But
This play a role, probably.
no, in high temperature, it's not.
Yeah, exactly. For the singlet, they play a role in.
No, for in the high temperature, it doesn't play a role. Yeah. In low temperature, yes.
There are people calculating that for higher.
Yeah, but it's hard.
Yeah.
It's hard. These disconnected contributions, they are hard.
Yeah, the contribution for computing the the disconnect diagram, the C, okay, is easier than the UD.
Sure, of course.
Actually, I can compute this with the noise method. Okay, but noise method is more approximate. Okay, so the chiral image, okay, even for CC bar, okay, when you increase the temperature, then it would drop to getting smaller and smaller. Okay, and that is what kind of the restoration of the chiral image. Okay, yeah. So with this chiral hierarchical restoration chiral image, then it would give indications to the pattern of the distribution of the hadron, distribution of mesons at high temperatures. Okay, so yeah, I also have the hierarchy distribution of hadron and also the hierarchy suppression of hadron in quark point plasma. Once it's dissolved, then we cannot see it in the detector, and that's the suppression. Okay? So this is suppression is in the hierarchy. Okay, that's something I feel interesting. Theoretically, the meson with the quark quantum Q bar Q, okay, say with different quarks or the same quark, whatever, okay, and it dissolves completely when the Q bar and Q become deconfined.
When you say dissolve, I mean the color confinement, deconfinement.
Yeah,
Color deconfinement.
Yeah, color deconfinement. Yes, exactly. And that's in the QCD. Only the QCD, okay, without any other interaction.
But how do you tell? You look
Yeah,
at
that's what I'm saying. I mean, we discussed during lunch. So far there is nobody have actually established formal connection between color symmetry versus color confinement yet. So why this symmetry? You said color symmetry has.
Yeah. Well, let me see let you see that. Let me go to the argument. My argument. Okay. Yeah. So the deconfined means that the screening mass, okay, defined in terms of the meson decorrelator, okay, yeah, of these two quarks, okay, in QCD interaction is bigger than its counterpart in the non-linear field theory, okay, that means with the phi quarks, okay. So in that case, then it is deconfined, okay, yeah, because the screening, okay, because when the screening, okay, getting smaller and then it would more attractive, okay, when the screening getting more and then the interaction between the color interaction between this quark anti-quark, okay, becomes smaller and then it will feed when it's bigger than the feed, okay. Of course, in the high temperature QCD, okay, you never have a phi theory because the QCD interaction is always there. Okay.
So how do you define screen mass at vacuum? What do you mean free?
Phi is the means that if I turn off the interaction of the QCD, okay, but the quark mass are the same. Okay.
So that's just the current mass.
Yeah. That's the current mass. The current mass.
You said screen mass.
Screening mass. Okay, I can still compute its correlator. Okay.
When there is no interaction.
Yeah, without interaction, I can still compute its correlator.
Okay. But that's just the current mass, is it?
No, not the same. Okay.
If there is no interaction.
Even with an interaction, okay, it's not the same as the current.
I know, but if there is no interaction, there is no screening anymore. Then that's the only.
There's no
only mass you
screening.
have is the current mass, right?
Yeah, you can say, but then there's still some subtlety, okay, due to say, for example, you have only at a very high temperature, then the gamma matrix of this Q bar Q is different, okay. It's the same, okay. Then say if I compute everything on a lattice, okay, then this can be compared, okay. These two quantities can be compared. I can just turn off.
Maybe would it be useful
to
move the conversation along a little bit so that we can see where this is going? Because I'm kind of missing, the forest from the trees, and so maybe if we let the speaker move on, it might be easy. Some of these questions might be clearer.
I think this is quite. This is the screening mass, okay, to describe, okay, whether this QV bar is deconfined, okay, is quite conventional.
I'm suggesting that I wasn't asking a question. I was suggesting that maybe you move on.
He said,
he
said I should.
Where you're trying to go.
You said I should shut up.
No. I wasn't saying that you shut up.
Don't get stuck
I was
on that
waiting for
point.
an equation.
Show us some more.
I can attach these ideas.
If you show us results, then we'll probably.
Okay.
I zip.
So the screening mass bigger than this, okay, and that is at the temperature, okay, this, okay, bigger than the chiral transition, okay, TC1, okay, So if at the temperature lower than that chiral transition, okay, then the screening mass, okay, will not be bigger than that, bigger than the phi. The phi non-inhibiting field theory, okay, the phi field theory, the phi quarks, okay. So that means the distribution always happens after the chiral symmetry of the QQ bar, okay, has been effectively restored. Okay. So the hierarchy of the distribution of meson is exactly the same as the restoration of chiral symmetry. Okay. So this is my case. Okay. Yeah, but to demonstrate this numerically, then I still have to compute the screening mass. Okay, and that is the what included in this talk. Okay, but this obviously okay, that's the case. Okay. So this implies the hierarchic suppression of mesons in the quark plasma, and which presumably can be observed in the relativistic heavy ion collision experiments such as LHC and the RIG. Okay, and I don't know where there's any experimental evidence for that. Okay, and here I recall there's a seminal paper by Matsui and Satz, okay, in 1986. Okay, say the distribution of the J psi in the quark plasma would result in the suppression of the production in heavy ion collision experiments. And this has been experimentally confirmed. Okay. Yeah. So let me discuss the relationship between the symmetry and the degenerates of the meson D correlator. Okay. So let me consider two quarks, Q1 and Q2. Okay. And the correlator, okay, from the 0 to x, okay, can be expressed in terms of computed by the quark propagator, okay, and meson D correlator is sum over x1, x2, and x3, x4, okay, and then the Z is the x3, okay, and the temperature T is the 1 over NTA, okay, NT is the size of the lattice, okay, in the x4 direction, okay. So the classification of the meson, okay, operator, say the scalar and the pseudo-scalar. Scalar is the identity, pseudo-scalar gamma 5, and a vector is the gamma 1, 2, and 4. The reason omit the 3 because the 3 is the direction of the propagation, okay, and so 3 is not counted. And then the AK is the gamma 5, gamma k. Tensor vector is the gamma 3, gamma k. And the axial tensor vector is the gamma 5, gamma 3, gamma k. Okay. So it's easy to know that, okay, axial means there's an extra gamma 5 in front. Okay. Now,
sorry, 1 second to understand this formula.
Yeah.
It's so you are taking the correlator with a periodic boundary conditions in time. So there is a short direction that gives you the temperature. And you are computing the correlation function around one of the spatial directions.
Exactly. Yeah. So the x, y, z, they are periodic, and then t is anti-periodic. Okay. Yeah.
Beginning planet temperature.
T.
Yes, the temperature.
Yeah. T. Okay. So if I have the UA1 symmetry, then the pseudo-scalar and scalar will degenerate, okay? And the tensor vector and the axial tensor vector, they are degenerate, okay? And if the SU2 cos SU2 chiral symmetry is restored, then I have the vector and axial vector, they are degenerate. Okay? So from the degeneracy of the meson D correlator, then I can tell whether the symmetry is restored or not.
This is a statement about correlators, not of states, right?
Just So
Space-like correlators.
One thing, the scalar part there means renormalization, right?
What means normalization?
The scalar, the S,
This S
is renormalized. That's my question, because in principle it needs renormalization.
Even normalized, okay, they will still degenerate.
No,
because the P is finite and the S is infinite. So
with the domain wall fermion, the utilizations are the same.
Yeah.
For the chiral fermions.
You are saying in the
No, but the P is finite. No? The pseudoscalar is finite because of the one identities. No? And the scalar.
CP and CS.
Well, they even without normalization, they degenerate. Okay. Yeah. Okay. Now, let me extend to the SU the QCD and of course, okay. So the restoration of the SUN cos SUN, okay, could manifest if I have this degeneracy for all favor combinations, okay. Yeah. So you have to go. You have your NF cos, then you have to go through all the combination, all pairs of this cos, okay, and then see if this degeneracy is established, okay, and the restoration UA1 symmetry of the then of this N quarks, okay, NF quarks will be required the degeneracy, okay, for all favor combinations. Okay? So we just go over all the subgroups, okay. Yeah. So now there's the relationship between the symmetry and the meson dissolution. Okay. So this is the screening mass. Okay. Yeah. The formal definition of the screening mass. Okay. Once I have the correlator, then I can compute the screening mass. Okay. Yeah. And then just do the fitting. Okay. Yeah. And then the degeneracy of the correlator. Okay. Implies the degeneracy of the screening mass.
Shouldn't that be a cosh instead of an e to the minus?
Yeah, sure. Yeah, you can use the cosh.
Because you've got a rebound resolution.
Yeah, if there's a finite lattice, but if the lattice is very large, okay, then doesn't matter. Okay, sure. Yeah, in practice, okay, if I have finite lattice, then I will use the cosh. Okay. So the degeneracy of the correlator implies the degeneracy of the screening mass. So the vector and the axial vector, they have the same screening mass. Okay. So that means if they dissolved, okay, at some temperature Td, then they will dissolve at the same temperature. Okay. So this is something that just because the symmetry restored. After symmetry is restored, then the vector and the axial vector will dissolve at the same temperature. Okay. So for example, the J psi and the chi C1 for the C bar C, they will be dissolved at the same temperature. And I don't know whether there's any experimental evidence or not. Okay. Yeah. Since the chi C1 may be not easy to detect, is the dissolution. Okay. Yeah. Similarly, for the UA1 symmetry, okay, the degeneracy of the scalar and pseudoscalar will imply the screening mass, okay, of the scalar and the pseudoscalar the same, and then they will dissolve at the same temperature, okay, and also for the tensor vector and axial tensor vector, okay, yeah, they will also dissolve at the same temperature. Okay. So, for example, the chi C0, okay, the the scalar, and this is the pseudoscalar eta C, okay, of the C bar C. They will dissolve at the same temperature. Okay. So again, okay, I do not know whether there's any experimental evidence. Okay. Yeah, I presume there's no experimentals in this one. Right? So how do I measure the symmetric thing? So I just measure it, okay, by looking at the difference, okay, and then normalize it by the sum, okay. So yeah, this without any normalization at all, okay. So if it's 0, then it's completely restored, okay, and it should be at any t, okay, yeah, not just at large t, okay, yeah. So this is the more stringent than the, say, asking the screening mass the same. Okay, yeah. So but this is some quantity, okay, then I will ask, okay, how small it is in order to say this is the restoration of Chiu symmetry. So that's a criteria, okay? So depends on this parameter, epsilon, VA, okay? And this defines the position of the SU2 cos SU2 Chiu symmetry, okay? So, so this carbon VA will not be suddenly become 0, okay? It will the temperature, okay, increase, and then it will smaller and smaller, and then then the restoration of Chiu symmetry, okay, depends on how small you want, okay. So if it's epsilon VA is smaller, then it will happen in a higher temperature. Okay. Similarly, for the UA1 symmetry breaking parameter, okay. So this is the I can use the scalar and pseudo-scalar, but in this case, I always use the vector, okay? So the tensor vector and the actual tensor vector, okay? The splitting, okay? To measure the Chiu symmetry.
We used 40 minutes so far.
Oh, is it? Sorry.
You probably want to hurry up, show us the data.
Okay, let me go to the action and algorithm, okay? So the quarks, I use the optimum to minimum fermion, okay, with the parameter NS 16 and lambda max over lambda mean is the 6.2 over 0.05, and the gluons I use the Pfeffer gauge action at beta, free beta, okay. But today I'm going to talk about the result of just one beta, okay. For free beta, in order to do the extrapolation to the continuum limit, okay. And for the one favor, I use the exact one favor algorithm, okay. And for the two favor, I use the two favor algorithm, okay. So this is the parameters for the gauge ensembles, okay. And the lattice size, okay, is 32 cube, the spatial, okay. And the time direction is 64, is corresponding to a 0 temperature. Actually, it's 48 MeV, okay. 16 up to 2, and the temperature is from 190 to about 1500, okay. Yeah. And statistics around 5,000 to 10,000 HMC trajectory, and the configuration is about 500 to 1,000 configurations. Okay, another spacing is determined by the Wilson fold. Okay, with these parameters. Okay, and the masses of the UD, S, and C charm core are obtained by tuning the bare masses. Okay, such that the lowest line state of the arm correlation function of this meson operators, okay, in good agreement with the pion, phi, and the J star, okay. They both simultaneously, okay, satisfy, okay, not just tuning one by one, okay. 3 of them tuned together. Yeah, so it's not an easy job. Okay. So now let me go to the meson T correlators, okay. So so this is the UD sector, okay. Yeah. At 190 MeV, okay. So this is the on the panel. Actually, I put 10 correlators, okay. Yeah. So pseudo-scalar, scalar, vector, actual vector, okay. This is the tensor vector, actual tensor vector, okay. But this is the fourth component, okay, and so okay. Yeah. And now you only see 5 of them, right? Because the others are degenerate, okay? They degenerate together, okay? So the guideline is this, okay? If these 10 correlators become 8 distinct correlators, okay? Because the V1 and A1, they are degenerate, okay? And also the V4 and A4 are degenerate, okay? Then this is the SU2 cos SU2 Chiu symmetry restoration. So 8 distinct correlators. Now, if it is further have the UA1, okay, symmetry, then only 5 distinct correlators. That means here there's a SU2 cos U1 has been restored. Okay, so from the correlator, the number of distinct correlators on here. Okay, then you can see the Chiu symmetry is restored. Okay, and if I look at the symmetry breaking parameters, so this is the U1 and then the SU2. Okay, and then the U1, okay, so U1 I have two channels, pseudoscalar and scalar, and then the tensor vector and actual tensor vector. And for the SU2, okay, is the vector and actual vector. Okay, so you can see, okay, the breaking is very small. Okay, yeah, you can ignore these two, another two parameters, which is related to the chiral spin, okay, symmetry, okay, which I have no time to discuss it today. Okay. Initially, I thought I can discuss it, but again, I found I don't have enough time to do it. Okay. So at high temperature, you can see the degenerates, okay, is pattern is changing, okay, and then you can see this is the breaking, it's getting smaller and smaller, okay, and then here, it converts to 3 different multiplets, and that is the manifestation of the chiral spin SU2CS chiral spin symmetry. But I will not talk about this today. Okay, so you can. Okay, you can see it, okay. As the temperature higher, okay, then it further degenerate, okay. Yeah. Okay. So this is the UD sector. Now go to UC, okay. Heavy and light sector. And then you can see the degenerates here is even more higher in the case of the UD, okay. Even at 190 MeV. And then okay, so now let's go to the charmonium. Okay,
Do you have results, let's say, at 140 below the transition temperature?
No, I didn't do it.
It would be interesting to see whether your charm looks the same or not.
Oh, not the same.
Well, how do you know?
Well, I have the one with the say the 48 MeV. Okay, so the zero temperature. You see.
Oh, you have done this. Okay.
Yeah, I think
Okay.
zero temperature. Yeah. Because I need the zero temperature result to tune the mass, physical mass. Okay. Now you can see, okay, at the 190 MeV, the symmetry breaking, okay, is very large. The SU2 and then the U1, okay. For the U1, okay, and yeah, this is the U1 and this U1, and these two channels actually are different, okay. And then for the SU2 channel, okay, so they are the breaking is large, okay, because the transport mass, okay. But if I increase the temperature, okay, then you see the breaking, okay, is getting smaller and smaller, okay. Look at these 3 bands, okay, three curves, okay, 3 breaking parameters, okay, getting smaller, okay. Higher temperature is smaller, okay. So this is the highest temperature. I go here, but then you can see, okay, it's still not completely go to 0, okay. But you can see, yeah, maybe at the high temperature, okay. But if you are looking, you're talking about the accuracy about say 5%, then certainly is below the 5%, okay. Yeah.
I'm sorry, can you remind me what is your kappa?
Kappa is the measure the splitting, okay, between
measure the splitting
of the same, okay, here, okay, splitting for the VA
okay.
is the vector and actual vector for the SU2. Okay.
Vector and actual vector.
Okay. So now I plot the result. Okay.
Am I right in assuming that if I had 3 non-interacting quarks, your kappa would always be 0? Is that right?
Okay.
If you have non-interacting quarks, 3 quarks.
Non-interacting quarks.
Non-interacting quarks.
Non-interacting quarks. Yeah.
Then kappa should be always 0. Is that
Yeah. Exactly. Yeah, I did not show you that.
No, I just wanted to calibrate.
Yeah, sure, I calibrate. No problem. Okay, so this is for the UD quark, and then for the same DT, okay, fixed DT at 0.5, 1, and 2, okay, and for different temperatures. So this is the summary or from the results, okay, of previous slides, okay, yeah. So you can see that for the V8, the SU2 cos U2 is chiral symmetry, and also for the U1 chiral symmetry. And then you can see, okay, it's getting small and small, 10 to the minus 7, okay? You see at the highest temperature, okay? And it was, yeah, and then getting small and small. And so is the US and US, okay? So, yeah. And so it depends on what position is the chiral symmetry you want. Then you get the temperature, okay? It stored. So for the S bar S, and then the U bar C, and then you can see the difference between the SS bar and the U bar C, okay? Yeah, this is at the same temperature, okay? This sector, okay, has a less specking, okay, than the S bar S. Yeah.
A question. So
Yes.
how much will the statistics influence your results? So, for example, if I have very bad statistics, it will be degenerate even at very low temperature.
No. Even the statistic, okay, then you have the larger statistic error, okay? It will not degenerate.
Oh, but the kind of the error bar over.
Okay, if the error bar, but you can see the error bar is yeah.
So I need to reach a good enough level of small error bar so that.
Yeah, but this is the easy, okay, because the error bar is the much less than the speed.
Okay.
So here is the same quark, okay, just a different Z, okay, CT, okay, a different DT, a different Z, okay, at the same temperature and a different T, okay, but at different temperature, then D will be different, such that DT is the same, okay. Yeah. Okay, so this is all the result, okay. Let me see here. Okay. And for the, you can see, okay, for the CC bar, okay, it really goes to a very high temperature in order to go down to breaking of 0.01, okay. Yeah, but it's getting smaller and smaller, okay. So there's reason why I say at the high temperature, okay, you would get whatever the precision you want, okay, to be the chiral symmetry. Okay. So to determine the TC, okay, is easy, okay. Say for example, you want the 0.01, then you just this horizontal line here, and then you get the temperature, TC at this speed, TT. Okay. Yeah. Similarly for the T1, okay, so it's easy to determine the TC and T1. Okay. But the points here, okay, is not the data point, so you need the interpolation and also maybe extrapolation. Okay. Yeah, it is beyond the range.
Wait, sorry,
yes.
I get confused. How do you get T1?
T1, okay. T1 is this, okay. For example, for this sector, SE, okay. So if your precision, okay, if I require the K of the parameter less than this, okay, and this is the 0.01. So for all the temperature higher than this temperature, okay, and the breaking parameters are smaller than the criteria, okay, and then yeah, so this is the T1, okay. So this is summarized the table, okay, all for all different sectors, for all different favor combinations, okay. So you can see, okay, for the chiral symmetry restoration of the UD and US, and then the UC, okay, here, okay, at GT is a 0.5, okay, and the DT is 1 here, okay. If I require the epsilon, okay, the 0.05 is 0.01, okay. So 0.05, okay, yeah, it is at lower temperature already attain such a precision, okay. If I require 0.01, okay, then it will attain the same precision at a higher temperature, okay, yeah. Okay, so for example, if I take the DT equal 1 and I take epsilon these two epsilon VA, epsilon TX, okay, for SU2, this for U1 is 5%. Yeah. Then the you can see below temperature 190 already restored SU2 cos SU2. Okay, at the for the U bar T. Okay. Now, and then for the SU3 cos U1, it would be at the 235. Okay. Yeah, because here, in order to have the SU3, then I have to go through all the favorite combinations of the UD and S. So that means include the S bar, and then the US, and then the UD. Okay. So here for the US, okay, is lower. So this is the highest. Okay. Yeah. So this is the temperature. Okay. And for the SU4 cos SU4 cos U1. Okay. So you can see at the so this I have typo. This should be C bar C. Okay. Yeah, and this is the 900. Okay. For the T1, you can T1 and TC is different. Okay. So this is the T. Yeah. Anyway,
is that typo? It should supposed to be CC.
CC. Yes. Yeah. There's a typo. There's a typo. Yeah. Sorry. Okay. Now if I change the the epsilon, okay, to a higher position, then I get the temperature higher. Okay. Yeah. So this is the here. SU2 cos SU2 cos U1, and SU3 cos SU3 cos U1, and then SU4 cos SU4 cos U1. Okay. So you can see this is the temperature. Okay.
Is the U1 visualization is more or less the same as SUN? The U1
and yeah.
Do you tell what
not you see this is the more or less the same. Okay, here you see for the same sector they are
TC
yeah TC and T1 they are more or less the same. Okay, yeah, sometimes TC is lower, sometimes T1 is lower. Okay, this is according to my data. Okay, but of course the data always suffer from the say the finite size effect and all this. Okay, so yeah, and the epsilon, yeah, sure. Okay. So so the conclusion is that in general, no matter how small are the epsilon VA, epsilon T6, picture of the hierarchic restoration of the Chiu symmetry in QCD with physical UDSC will persist. Okay. Yeah, even though you give me a say 10 to the minus 6, okay, then it will still manifest at high temperatures. Okay. Yeah. So yeah. So this is the relation I got. Okay. And then yeah, I think the most interesting, the SS bar, okay, is the higher temp. This restoration is higher than the U bar C sector. Okay. Yeah. So it's not just ordinary according to the port mass or the mass of the meson. Okay. Okay. And I think this will automatically implies the dissolution is the same hierarchy as this. Okay. Yeah. If you agree, okay, the meson dissolution must be at a temperature above, okay, the TC and T1. Okay. And it should not be too far above the TC and T1. So this gives me the hierarchic suppression of hadrons in the quark 1 plasma. And presumably this can be observed, okay, even though experimentally it may be very difficult. Okay, so let me conclude. Okay, so I can get in time. Okay. Yeah. So yeah, just summarize. Okay. Yeah, this study obtains the hierarchy of the restoration Chiu symmetry in the NF2 + 1 lattice QCD at the physical point. Yeah, in this order. Okay, so this is the numerically obtained, and the ordering of these two is completely unexpected. Yeah, so these are the first results in lattice QCD. Yeah, and I think this, so this, because this hierarchy, okay, then immediately give me the hierarchic restoration of Chiu symmetry from the SU2 cos SU2 cos U1 of the UD sector to UD quark, okay, to the SU3 cos SU3 cos U1 to the UDS quark, and then to SU4 cos U1 of the UDSC quarks, okay. Also the hierarchy of the dissolution of hadrons, okay, in this order, okay, and also the same hierarchy for the suppression of hadrons, okay, and which we can be observed in the ion collision experiments. Okay. So besides that, okay, I would like to also point out this: the restoration of the SU2 cos SU2 Chiu symmetry implies the vector and axial vector with the same vapor content, okay, they are dissolved at the same temperature, okay. So this is the coming directly from the symmetry, okay. As long as it's restored, then it will be dissolved at the same temperature. So there's the J side and the Chi C1, they are dissolved at the same temperature, okay. This can be verified in experimental way, okay. Yeah. And restoration UA1 symmetry, okay, will imply the dissolution, okay, of the meson of the pseudoscalar and the scalar with at the same temperature, and also the tensor vector and the axial tensor vector will dissolve at the same temperature. So you can look at the Chi C0, the eta C, okay, they will dissolve at the same temperature. Yeah, yeah. I hope this can be experimentally seen, okay, in the future. If not now, okay, okay. Yeah, thank you very much for your attention.
Questions?
Sure.
Yes.
See, I was thinking, I would actually predict that TUC gets smaller as you make MC bigger. I don't know if you have
MT.
TUC.
Yeah, yeah.
I would predict that to get smaller as you make the charm quark mass heavier. Because I was thinking about that, I think it doesn't.
Because this is a heavy light system.
Yeah, exactly. I think it's the light quark which is doing the most.
Yeah, I think this is the light quark. Yeah, yeah.
And that's why it's less than TSS bar. So I think as you make MC heavier, that temperature would I would predict it would get lower.
Can you evaluate this?
No, this is just some intuition.
Okay, just an intuition. Okay.
Wow. I mean, well, no, actually, I think as you make MC bigger and bigger, you can use heavy quark effect theory to derive this because you give. I think the spectrum of the parity partners will start to get 1 over n suppressed, and so you'll approach a limit where you have a heavy quark flavor symmetry. That
okay.
That would be my guess.
Yeah, good. Yeah, thank you.
We have an online question.
Yeah.
Go ahead.
That's the online question.
Okay. So my question is the current quark mass will also break the chiral symmetry. So why not that will give a non-zero symmetry kappa? So why kappa doesn't influenced by the current quark mass?
Your question is why the kappa getting smaller, is it?
Yeah, I mean, for example, C quark is the current. Its current quark mass is very heavy. So that will also break the chiral symmetry. So that value should also contribute to a non-zero kappa value. So why your kappa value doesn't only depend on the quark condensate, doesn't depend on the current quark mass from the heavy quarks.
Yeah. Well, this is the result I got. Okay, and the reasoning is that at the higher temperature, then it has this thermal energy, of the quark, When the thermal energy of the quark, is much bigger than this rest mass energy, then the rest mass, large or small, will be irrelevant, So that's the reason why it has the same symmetry as the massless fermi.
But that means, if to follow up on this, that what I said before and what you confirmed may not be right, that for free quarks with different masses, your kappa should not be exactly 0. It should be finite because I have the symmetry breaking in the mass spectrum. Yeah, and so that would be the calibration. I look for a calibration because you have a kappa is 10 to the minus 2, 10 to the minus 2. what compared to what, right? So if one has the value for non-interacting quarks, then I have sort of
You see,
a gauge.
for the free fermion, okay, without any interaction, the Chiral symmetry is exact.
No,
But
if you don't have
there's
different
a mass,
quarks.
if there's a mass, then no, there's
Exactly.
no, yeah, there's.
So in principle, you should be able, that means probably even I would be able to calculate this, your cutoff for a free theory.
Yeah,
just
yeah,
with
yeah,
different
yeah,
masses,
yeah.
right? And then
I have the data, I just don't show.
Yeah.
Okay. Yeah, actually, they are, you see, if I look at the free fermion case, okay, and I go to the high temperature, okay, it does not go smaller and smaller.
Yeah, eventually. Well,
Yeah, it does not, unlike the case of QCD. For QCD, okay, it would stop. But for the free fermion, okay, when I go to high and high temperature, okay, it's getting smaller, but not as smaller as the with the QCD interaction. Yeah.
What do you mean you have the data? I was confused. I thought Volker was asking about non-interacting quarks. What do you mean by I have the data
Yeah, I have the data, but I did not show you
for non-interacting quarks?
for for the free fermion, for the free quarks. Yeah.
Mass influence, right?
Yeah, with the same mass, okay, with the same mass. Say with the same charm mass, for example, so for the C, okay, and then the is
It's 3 level, no? You just put the links equal to 1.
you can calculate this for the piece of paper. essentially.
Yeah, with the link, with the link to 1. Okay, yeah, and then I can compute. Yeah.
Your UC, your TSC is larger than TUC, right?
Yeah.
So then that will argue against your argument.
No, his argument is using the one is very light, one is very.
I know.
light, yeah.
Well, it's
But the S and C, okay, it's not as dramatic.
No,
No, I'm talking about you. You're talking about UC
UC
versus
is
SC.
but
No,
the S is still light enough that it's impacted by the dynamics.
S is heavier than the.
No. The point is S is light enough that it's impacted by the dynamics.
You mean you're saying the S is not heavy enough?
Yes.
Yeah.
Whereas
Oh,
C has done heavy
When you say
enough.
heavy enough, which scale you're comparing to? That's why bothering me
Lambda
here.
QCD.
There must be some scale you're talking about when you say heavy or light,
Yeah,
right?
I don't know.
Lambda
Heavy
QCD.
proximity.
Or lambda.
Lambda QCD. Like when C, this charm quark is barely heavy enough for heavy quark effective theory to work.
Or we can calculate the B.
Exactly.
Yeah,
So
yeah.
I think TUV will be less than TUC. That's my prediction.
Yeah.
And then we can see if, well.
Yeah.
On the technical side, many of your results depend on the simulations where the discretization in the time direction is just 2 lattice points or 4.
Yeah, there's a high temperature, yeah.
You are not worried about very large cutoff effects there? With 2 lattice points, it can be non-monotonous.
Yeah, actually, I have the different lattice space, different beta. Okay, I can.
Yeah, but the others are coarser, right?
Yeah.
So if they are coarser, it would be even worse. No, you have. My question is, do you have finer lattice spacings? I thought that what you show us is the highest beta.
That's the highest beta. Yeah.
So this is the finest lattice spacing.
Yeah, the finest.
But
lattice
still
spacing.
there is only a couple of points. So. Yeah.
Sure, this has to be very hard. Thank you. Yeah, but I think at this high temperature, okay, that depend on that.
Well, your temperature is at the scale of the cutoff.
Well,
it's up to 2 times. 2 times.
Yeah, sure. All the
1 over 2 is similar to 1.
yeah.
0.
I guess will it make sense to use some shortcuts?
Might be, yes, might be a good idea to have a finer discretization time, but you need some level up in the temperature direction.
On the other hand, just your definition of Chiral symmetry is a very narrow definition. You're only looking at like the symmetry between pseudoscalar scalar vectors, pseudo vector, right? Actually,
Yeah.
But But normally in general sense, the chiral symmetry is not only between the same flavor, but across flavor. For example, there is a symmetry that you will not have. Like for example, the symmetry between CC bar versus QQ bar. I mean UU bar, for example.
Why this is because these are not two different.
If you talk about, for example, the U quark and D quark, in the U quark, they're both very light. So there is symmetry among different flavors, right?
Yeah, but then about the you see.
So I'm saying your symmetry, your definition of how symmetry is very narrow definition. It's only on the same flavor level. You can never have symmetry between different flavors, right?
Different flavor.
Because you have different mass.
Yeah, but then if I go
even at the high temperature,
Different temperature.
or even but not at
temperature,
this temperature we're talking about.
High temperature. You see, when you go over all the sectors, and then you can see, okay, this. So you see, for example, you have the TS bar, okay, is a 235 MeV.
And then you look at CC bar, which
is
different.
CC bar different, okay. Yeah, different. But then
so there's
then that means if I have a higher temperature than 900, then everything is smaller than that. Okay, then there's the point. Then there's reason why I call it above the this temperature. Okay, then I have the SU.
Okay, so this you can test. For example, for suppose you have very high temperature like 1 GeV.
Yeah.
You look at your correlator. The correlator, the difference between SS bar versus CC bar, for example, the correlator are the same.
Not the same, of course, not the same.
I mean, how big they are, the difference.
Well, you can see, okay, the
versus on the difference between the same flavor.
Yeah. Say, for example, you have the okay.
But this cover only you only compare cover to the same flavor. Right? You never compare cover between different flavor.
Yeah. Why I don't have to compare that, because if I get this chiral symmetry restoration for each favor combination, then is the entire.
That's what I'm saying. Yeah, you're only looking at the same flavor.
Yeah. Then it's sufficient. That's the okay. So you are asking this question. Okay, when I have the.
I mean, of course, if you go to infinity, everything is the same. Yeah.
No. Here. Now you're asking if I have n quarks. Okay. Then I have looked at this chiral symmetry, okay, for all favor combination, okay. So this is for SU2, cos SU2 chiral symmetry restoration for all favor combinations, okay. And then this will imply the SUN cos UN chiral symmetry restored, okay. So I do not need to examine all. Yeah. So this is the you see. Does this answer your question?
Yeah, I agree completely with you. Yeah, sure.
Yeah, but I do not necessarily to compare, okay, the correlator of the C bar C and then the U bar D, okay, yeah, because it's not needed to assert the chiral symmetry of the SUN cos SUN. So.
All right. No more questions?
Thanks.
I get more of this.
Yeah.
So good.
Are you